Hello, everyone. We'll give everyone a few minutes to jump on. How are you, Justin and
I'm
Floyd?
doing great. Thank you. Thanks for asking, Angela.
I'm doing great too. Doing great. Another great day in my paradise.
Been a little while since we've all got to meet together on a
Yeah.
webinar.
5 minute, yeah.
Yeah, we were just reminiscing on how long ago that was, right? Wow.
Yep, it's been a while.
Hello, Mohammed. Hello, Monish. Sorry if I'm messing up the names. Good morning, Shalene. Our beautiful Shalene in the background. Hello, Shahid. Anderson. Good morning, Anderson. All right. This should be a really good one. All right. Hello, everyone. And once again, thanks for joining us. I hope you all are having a great day and ready to hang out with myself, Floyd, and our guest, Justin. They will be discussing predictive analytics for heat exchanger bundles. As always, this is definitely an informal webinar, so we love engagement, ask questions. Hello, everyone. I see everyone is already kind of engaging. That's great. Please drop all your questions in the chat. We will also have our first poll that'll be coming up right now. And then we'll have a series of 6 polls this session. So I'll interrupt and ask you guys to answer the polls throughout the webinar. All right, let's get started. Well, I am Angela Saldivar, Antea's Asset Integrity and Risk-Based Inspection Specialist. I have been in the asset integrity and risk-based inspection world for over 10 years now, working on MI projects from start to run all the way to maintain. So I help our clients even after we get the project completed. Justin, you want to go ahead and introduce
Sure.
yourself?
Thanks, Angela. So I'm Justin Daarud. I'm Director for Asset Integrity and Reliability at Cognascents Consulting. So I've been doing asset integrity for over 16 years now. And that was, a lot of different hair involvements happen, but lately it's a mustache. So thanks for having me today. I'm excited to talk about all this.
Thanks so much, Justin. We also have Floyd here, of course, with Antea, and he's going to, give a little story about himself and a little bit about Antea as well, and how we help with asset integrity management. Go
Hey,
ahead,
thank you,
Floyd.
Angela. Yeah, my name is Floyd Baker. I've been in the asset integrity management industry for my entire career, 40 years. About half of that career was on the owner user side of the business, the other half on technology side, which is where I'm at now, the software that manages all this kinds of data. Um, Antea is a asset integrity management RBI platform that actually manages all sorts of assets, pressure vessels, pipes, tanks, PSVs, but also other assets. We actually manage over 240 different types of assets that operate in a plant, in a facility. We've been around for 34 years. Our first customer was Exxon in Italy and still is today. We've had zero turnover in that 34 years. We're new to the U.S. or to the North America. Probably, I think we started up here about 4 years ago. And yeah, we're just enjoying our stay here.
Thanks so much, Floyd. Well, Justin's going to kick us off. He's got a lot of great stuff to go over with the heat exchanger bundles. So go ahead,
Cool.
Justin.
Thanks, Angela. Thanks, Floyd. Well, I appreciate the time that everybody's spending with us today. I wanted to do a subject that was relatively interesting to me, as well as would involve a bit of math and math techniques that we don't necessarily use all the time. And I wanted to try to solve a problem that we tend to deal with in the integrity industry and doing all of our integrity engineering practices. Before I really get rolling, I just wanted to explain the why I'm here today. I've been engaged with Floyd and the team at Antea for quite some time, and we always kind of problem solve some integrity issues here and there. And I really appreciate the Antea team for asking me to be a part of this and really try to dive into something that I have a little bit of passion about. So we'll go ahead and get rolling. So we had multiple objectives that we put out to try to gain some influence and get some individuals to come and see what we have to talk about today. So these objectives, a little wordy, but essentially we're going to try to apply some mathematical principles for predictive analytics to be able to understand exchanger bundles a little bit better in the integrity world. So we're gonna look at some inspection samples and try to uncover how do we predict from those inspection samples the bundle life to be able to boost our bundle lifespan, essentially coming from those inspections on those tubes. We also want to look at some of the predictive powers of predictive analysis or analytics. When we start looking at specific inspection results, I will jump into some math, but I'll try to explain it at a high level so that I can reach all the audience that's with us today. Then we're going to take that information from what we learned from an inspection and those predictive analytics that we're going to use, and we're going to push that into an RBI process. And how we're trying to unlock a bit of the RBI process is to show you on the front end, there's some analytics and predictive things that we can do while also strengthening our risk and reducing our uncertainty in our risk when it comes to a heat exchanger bundle. There's a bit of a gray area out there for heat exchanger bundles. Hopefully we'll try to make it a little bit less gray today. And then from that standpoint, once we have some risk predictions, we're going to look at risk thresholds. We're going to then look at a scenario of how we utilize that risk to be able to do our inspection planning and optimize our inspection plans. And then we'll wrap it up at the end to show you the whole process and summarize, how does predictive analytics potentially help us throughout this whole process. And forgive me if I get a little mathy here and there. We do have some spots where I'll be able to take a break and be able to take a breath and get back into layman's terms, but let's go ahead and get rolling here. So what was the problem? What was the situation that I was trying to think about and try to solve today? So using predictive analytics is something that's near and dear to my heart. I really want to lean on proven and tried and true mathematical principles to help us in the integrity engineering world within our asset integrity and reliability space. But can we use predictive analytics on heat exchanger bundles? I think we absolutely can. But what does that get us? Well, it can minimize costs by helping us predict some of those bundle lifespans a little bit more accurately. It can help us enhance our risk by trying to reduce that uncertainty in our risk results. And then we can optimize how are we going to manage and inspect that bundle as we go throughout that bundle's lifespan. So we'll have some examples around that. And a lot of the principles and information I'm talking about today, there is a lot within API 581, which is the quantitative essentially the methodology for risk-based inspection. There's a lot of these principles kind of paralleled within there. I do utilize some other techniques, but API 581 has a lot of good information as far as the mathematical principles within that section of the document.
Solid basis to work from. I like that.
We'll go ahead and have our second poll. And how can we use predictive analytics for tube bundle inspections?
Awesome. So we're going to look at an inspection that was done on a real bundle. And we're going to utilize that information from that inspection sample to be able to predict what our potential wall loss could be from a situation that we have in real life. So here's our tube bundle scenario. This is an actual bundle. This is actual inspections that were done. This is an eddy current inspection completed on a bundle. They went out and they inspected approximately just over 99% of the tubes. And it's a lot of tubes to inspect with eddy current. We found that 33 of those tubes have a wall loss of just around 45% or less. And so we do see some corrosion rates associated to those tubes. That ended up calculating to a corrosion rate of 1.3 milli-inches per year. And industry inspectors and integrity engineers, we just say 1.3 mils, or we're implying milli-inches per year. So typically on a traditional way to kind of manage our bundle, we want to figure out what's the remaining life of the bundle, based off that remaining life, let's set our next inspection interval and let's just run and gun from there. But what about the 4 tubes that were not inspected? What do we do with those 4 tubes? Yeah, plug them, do all those kinds of things. But I wanted to take this opportunity to do something else. What was that, Floyd?
I said plug them, but I agree with you. You should take that next step.
Yeah, so plug them, move on, all that good stuff. But I want more insight. I want to gain a little bit more knowledge about my bundle. So let's see, can we use predictive analytics for those 4 tubes? So let's run through a process here. So from that, we have 544 tubes that we have results from. We have information, it's good quality information, but I don't have information for those 4. So how do I quantify with a high confidence to try to reduce how much uncertainty I have in those results? How do I quantify what could have happened for those tubes? Can I predict a corrosion rate associated to it? So let's see what we found. With those 4 tubes, less than 1%, it's actually 0.2% of the tubes, we're going to try to predict that corrosion rate. So we're going to use some mathematical principles to calculate the likelihood of our corrosion rates associated with those 4 tubes. And since we have all that data, it's going to be a little bit easier for me to understand what is going to happen with those 4 tubes. If I only inspected 4 tubes and I had 544 that I was trying to predict, that's a different ball game. That means I have a lot of uncertainty. But with those only 4 tubes, I actually have a little bit less uncertainty than I'm too worried about. So let's go ahead and jump into some mathematical analysis and see how things go. And this is where it's going to get a little heavy from a math perspective, but I'll try to keep it high level. So what we're doing here is we're using some confidence, and a term that I like to say is confidence-based inspection. So we're using some confidence to generate a confidence interval associated to a probability distribution that we're applying to predict what our corrosion rate may be. I said a lot of longer words. Essentially, if you think of a bell curve, and you think of any statistics class or the poll that happens out there, you have the mean, you have the averages, you have all that stuff. But we're talking about a bell curve. Typically, the majority of your results and readings are going to lie somewhere within a shape of a bell curve. The tighter that bell curve is, the more results are right there in that mean. So if you can see on the right, I have a graph here that's a wall loss rate distribution graph. That blue line that you see is a bell curve. So right in the middle, down at the bottom, you see little X's. Those are all my readings that we found from the inspection. But what I'm trying to do here is I want to set up a confidence interval. So I want to be really confident in making a prediction. So I have a confidence interval of 99.8%. Out of that 99.8%, I have 0.2% uncertainty. So what I'm trying to do is go, hey, I've got the top 0.2% of that bundle that I didn't inspect. What could be the potential corrosion rate based on everything I know? What could be the potential corrosion rate of those 4 tubes? And I want to be 99.8% confident in it. My results came back saying, hey, it's 1.43 mils per year. Okay, not a big difference between 1.3, but it's 1.43, so it's a little bit higher. Now, my gut as an integrity engineer would say, hey, let's just assume it could be higher and call it good. But I can't back that up with math, right? I can't back that up with something. So what these graphs are showing us, the one on the left side, is this is a likelihood distribution. You see that little colored spot down there on the bottom. That colored spot is showing me my potential uncertainty with the results that I have. If it's a big colored spot, I have more uncertainty, right? So I'm not able to predict with a lot of accuracy my results from a confidence interval. But because that spot's pretty small and nodular and not diffuse, I am able to predict a pretty good assumption and pretty good prediction based off of my corrosion rates. And that's what that bell curve is showing again. The tighter it is, the more information I have that lines up to where my mean and averages may be. So I'm going to have a better understanding of our corrosion rates.
Your mute is on. You're on mute.
So
poll 3, and were the inspection results favorable, and do we have confidence in those results?
Thank you, Angela, coming through for me. So were the results favorable? Yeah, we have quite a bit of information. We are able to predict something, but let's go ahead and take that to the next step. So let's try to identify our remaining life for those tubes of that bundle. We have 2 different corrosion rates. What does that really mean? So in determining our remaining life, we're going to go through the remaining life calculations for figuring out our design minimum thicknesses using ASME, etc. But the 2 corrosion rates, the observed corrosion rate of 1.3 mils per year, and then our predicted corrosion rate of 1.43 mils per year. Not a big difference if you're talking about a very short lifespan of the bundle. You know, it's brand new, we just did an inspection, but this bundle is roughly 20-some years old. So that can make a big difference. So if you see there, the remaining life of the corrosion rate that we observed was 17.62 years, and our half-life was around 8.8 years. But if we look at the corrosion rate that we predicted, that ends up being 13.75 years with a 6.8 half-life. So that's 22% less. If I'm going and setting my inspection interval on that 8 years from that half-life from the observed corrosion rate, instead of the 6 years from my remaining life, that's a relatively big difference. 2 years is a pretty long time in the grand scheme of things. So I might not have the right interval set up if I'm not doing a little bit more analysis and maybe paying a little bit more attention to those tubes. Yes, I could have plugged them, but again, this is a good example and we're trying to show how predictive analytics can work. So I've got my corrosion rates, I've got my remaining life calculations. Following API 581, where we were talking about using a Weibull distribution for figuring out the probability of failure for our bundles. Don't have to be an expert in Weibull. I'll try to explain it really high level. but there's two parameters that I'm really concerned about from a Weibull analysis. That's my shape factor, or beta, the little b that you see there, and the characteristic life, or eta, which is that n. So the shape factor, think of it as this way. The shape determines how quickly my reliability drops off and or how quickly my probability of failure increases. Okay, a really high shape factor means I'm dropping off a ledge. A really low shape factor means I have a predictable long-term reliability decay, for instance. And as far as characteristic life, this is the parameter that helps us determine mean time to failure. Essentially, how long is that bundle expected to live? Okay, so the longer life, the longer the bundle is going to work within that process service. So API 581 suggests multiple different methodologies for determining a beta as well as an eta. I'm using a different methodology, but it's very similar, using probabilistic math. So we're trying to figure out, how do we find our shape factor and our characteristic life from the data that we know from those corrosion rates and the remaining life. So on this example, this is using a beta of a 3.0 and a characteristic life of 20 years for that bundle. We're expecting it to actually be in service for 20 years. So this is the reliability distribution plotted out on a graph. The green line you see there is the reliability of the bundle. The orangish line that you see going up from the bottom left to the top right is your probability of failure. And across the bottom area is your probability density function. So what we're seeing here is when you put your bundle in service, on the far left side, it's high reliability. But as the life of that bundle goes on, it ends up being less and less reliable. So that's what that decay looks like. So we're trying to see the difference between our shape factor and characteristic life based off of what we have observed for the corrosion rate, as well as the predicted corrosion rates. In order to do that, we want to do an analysis of beta and eta. Okay, so we have the beta and eta that we just looked at, the shape factor and characteristic life. There's our probability density function. You can see the bell curve there. But now with the new information that we have associated to a database of information that we're using to plot this information against, so it's legit information and legit data, we're trying to predict what's our new beta based off of that bundle itself, looking at our observed corrosion rate as well as looking at that predicted corrosion rate. So on the left, you can see that bell curve. Then you have a red line, a blue line on the left, and a black line on the right. That red line is our mean of the new posterior, or our analysis conducted on that beta. You can see it shifted slightly to the right. If it didn't shift at all, that red line would be right there in the middle with that 3, but it shifted slightly to the right, giving us a little bit less reliability from that shape factor. But if we look at the eta, which is the characteristic life, so how long does that bundle actually last, for instance, that eta shifted quite a bit to the right. So it's quite a bit more impactful change. We're expecting a longer life out of that bundle. So if we take that information, the betas and etas, we plot them together, do a lot of different combinations, we figure out how long a characteristic life, what's our mean time to failures, all that good stuff. This is the pretty graph that we get when we look at just reliability. We're really reliable at the beginning, we're less reliable towards the end of its life, and now we have a combination of a lot of betas and etas. Well, what does that mean? We want to take this information and we want to use the beta and eta to figure out our probability of failure using that Weibull distribution. So let's go ahead and select some betas and etas that we can look at from a risk perspective to plug into a RBI tool such as Antea, of how does that risk come up a little bit differently so that we can do some inspection planning associated to those betas and etas. So we're going to select 2 different shape factors and characteristic life combinations. And we're going to take that and we're going to plug that into some RBI analysis.
Poll 4, how do we apply these results to RBI?
Thank you, Angela. So now that we know our betas and etas, let's see the difference of what those combinations actually mean and how does that actually influence our risk. So we'll break it into a bit more of a risk matrix and understanding of how we're going to guide those principles. Okay, but first, before we get into that, just make sure we're all on the same page. What is risk? So a lot of different definitions for risk, but they all are roughly the same. Probability of failure times the consequence of failure. What that means, general definition, it's the possibility of a loss or an injury, potentially. Something creates a suggested hazard of some sort. Essentially, we can take all that information, we can plot it on a risk matrix. In this example on the top right, we just see a 5 by 5 for a graphic's sake, probability on the y-axis, consequence on the x-axis. If we take and paraphrase the API 580, which is the RBI documentation for the high-level methodology, the risk is a combination of the probability of some event occurring during a time period of interest and the consequences associated with this event. So what's the probability of that bundle actually failing, and how bad could it fail? One quick note about bundles. Bundles behave a little bit differently than a regular pressure vessel, for instance, or a tank or whatever. Bundles are typically driven by financial loss. Doesn't mean that there's not a safety and environmental impact, but typically it's a financial loss, because when a bundle fails, that tube fails. Okay, so we're defining that failure as a tube leak. So if the tube leaks, you're either losing product or you're losing cooling water. You have a financial impact of one shape or another. So we're just looking from a high level. Bundle consequences are typically a financial or efficiency loss that affects the process that bundle is actually trying to achieve. We're not focusing on consequence failure today. It's purely on probability of failure at this point. But if we take the information from our Weibull analysis, and we have those new parameters there, we have two different Weibuls that we're going to run into our RBI and our probability of failure calculations. So we have Weibull A and Weibull B. So the A is 3.09 for our shape factor and a characteristic life of 25.1. And Weibull B is a shape factor of 3.99, quite a bit different, and our characteristic life of roughly 25.1 again. So let's go ahead and calculate that risk. So this is some screenshots from Antea. One of the things I really like about Antea is the configurability and the possibility of using multiple different things to be able to see all these differences. So I tried to summarize a lot of those different calculations that we did utilizing the beta and eta function within the probability of failure Weibull distribution. And we were able to produce a lot of those different results. But I'll let Floyd kind of jump in here real quick. Give me a break for some water.
Yeah, sure. Well, I mean, you make a good point there. I mean, I've seen a lot of RBI tools that people use. And one of the most important things I find, or one of the most valuable things I find with Antea's, with our solution, is the fact that it is configurable. You're able to, flexibly configure your individual risk, calculate your probability of failure, consequence of failure, failurable, and they're configurable inputs or user defined, so to speak. So the calculations can take place, but yet a user can adjust those to the real world situation.
Yep, definitely. And that's a super strong feature, because with not a lot of tools allow me to go in and manipulate individual aspects that are helping me flex and see the sensitivity of my analysis. And Antea really supports that, which is really nice. Cool. Thanks, Floyd. So let's jump into our RBI results plotted on a balanced risk matrix here. So the before and after. Before means, hey, before I went out and did that inspection, where was my risk for that tube bundle? You can see that it's all at the top of the risk matrix, which is probability of failure of 5, which is the highest we can have for that probability of failure. So on the left for Weibull A, we see the shape factor and eta there. It was pretty high risk, but after we executed the risk did drop down one level. We were able to see, based on the results, what the remaining risk is, which helps us kind of determine what kind of inspection plan we may or may not want to do. With the Weibull B, the risk it did drop a bit, but not as much as the Weibull A. So let's go ahead and look at these differences a little bit. So if I look again at that Weibull distribution that we had with the different characteristics, that black line that you see there, that's the life of the bundle. And then that blue line that's just appearing, that's essentially what we're looking at for those two different shape and characteristic life combinations. But along that blue line, we had our risk before ended up being increased as far as the reliability, or the risk ended up decreasing from the probability of failure perspective. So this isn't 100% accurate. This is just more for illustration's sake. But before, the A and B did actually reducing the risk quite a bit, because we did understand it. But that red line you see going across the middle, that's the 50% mark. That's essentially where that probability of failure from a 4 becomes a 5. So let's go ahead and look at this. So now we know our risk. We understand what's going on. Which one are we going to end up picking, and why? Angela.
All right, we have poll 5. The risk has now been determined. Now when and why should we inspect?
So we want to find out what our risk threshold really means. We want to create and optimize those inspection plans based off of our risk, and then we want to streamline our bundle maintenance associated to that risk and the inspection plans. So what you see here is that first Weibull distribution, but we see some extra lines there. Those lines are helping us determine what the probability of failure categories are based off of that Weibull distribution. The table 8.6 from API 581 helps us with that definition. You can see probability of failure of less than or equal to 0.1, which is where that green line is. And if you go all the way down to the red line, which is the 50 mark, so 0.5 to 1.0, that's where, if you look at the reliability set of that function from the reliability of 1.0 down to 0, that's how it drops down or increases in probability of failure. So this is just a visual example of how that all works. Now, when it comes to setting risk thresholds, this is very much so a owner-operator's input. It's up to the owner-operator to really feel where are they comfortable when it comes to inspecting bundles, managing the risk of those bundles, and what you want to do from an integrity and inspection plan perspective, maybe even maintenance, etc. Notice we're not focusing on the consequence of failure. There is consequence of failure categories. Right now, we're just focusing on probability of failure. So we know our risk. We understand where those thresholds are when it comes to the Weibull function as well as the probability of failure. What does this really mean? Well, with our risk, I want to go out and do my inspection plan now. And on the right is a bit of a process flow there. And this is really kind of tailored towards the Antea tool because it's got a real powerful inspection planning process when it comes to RBI. So you have your risk, you then set what are my thresholds. I have a target risk I want, I have a target damage factor, I have a target date that I want to perform the actual inspection. I then have a risk calculation projection. When will my risk reach those thresholds that we set up? And then I want to review what those inspection suggestions are, and maybe I want to tweak it here and there. There's an automatic push or there's a manual push to those inspection plans that I want to manage. And then I want to go ahead and complete what my projections are and what that inspection plan really means. So there's a lot going on here. I'll break it into 2 more slides on the next one. But essentially, we're going to schedule our inspections based off of this process. So API 581 categories for risk. I wanted to show one more graph on the right from figure 4.5 when it comes to API 581. This is the example ISO risk plot. So it shows you a little bit differently. Instead of being colors in different squares, those are your ISO risk lines of where your risk categories can change based off of your consequence of failure. So this section, this is the inspection planning, essentially what I just talked about, but it's broken out using Antea and how Antea works. And this is one of the really powerful pieces of Antea that I really like when it comes to being an RBI person and doing integrity engineering. On the left is that flow chart that I went over before. On the table next to it is a example from a RBI study. This is not the bundle, but this is a different vessel just to show the uniqueness of this inspection planning process. You set your target dates using Antea. So I have a target damage factor, let's say 500, I have a target risk of 5, and I have a target date associated to when is that risk going to be exceeded, or when is that damage factor to be exceeded based off of those 2 different thresholds. Over on the right side, I have 3 risk matrices. I have a now, I have a future without inspections, and I have a future with inspections. So bear with me, there's a little bit, it should make more sense here pretty soon. So the now risk is what's my risk today? And then down below that, I have a risk number and I have a damage factor that's associated to how that piece of equipment is failing. So the risk number is 2.4 and the damage factor is 5.3. If I look over at the future without inspections, my risk goes up to 103 and my damage factor goes up to 230. So my threshold has been exceeded. Then if I go over to the right, future with inspections, I have a risk of 6.39 and a damage factor of 14.1. Essentially what that means, looking at the table, I have my target set up. My future without is, hey, can I make the next 13, 14 years with this piece of equipment? Let's go ahead and evaluate where is my risk going to be at that date. And that's what that middle risk matrix means. And then the bottom section, future with, this is, well, if I have those risk thresholds, but I want to reach that date, what date between now and then, if any, do I need to perform some inspections to be able to reach that future date with those risk thresholds? So that's what this graph shows. So on the next slide, we have the second half of that. So I have my now, future with, and future without inspections. So I didn't reach that 2036 time. It ended up asking me to do inspections in 2027. So that's what the next two bottom tables show me. So my plan is I have damage factors associated to that risk. I need to go out and inspect that damage factor. At the bottom, it says, hey, I need to do highly effective inspections for both of those damage factors in 2027 if I'm going to be able to try to reach that risk projection of 2036. So in a nutshell, utilizing the Antea inspection planning process with all of my risk projections and the ability to configure all of my different risk thresholds on an equipment or component basis, it allows me to be very targeted on my inspection plans and how I want to manage my inspections. It's awesome. I love using this piece of the tool. I can also go in and say, you know what, we're having a turnaround in 2 years. What if we did a highly effective inspection in 2 years? How does that affect my risk? And I can also play around with all that. So the configurability is sweet.
All right, we have our final poll 6. Can we incorporate additional predictive analytics into our risk-based inspection planning? Justin?
Yes, I think we absolutely can. So let's explore that. We've just gone through quite a bit of math and I'm trying to explain how's Weibull work, how are we doing these bell curves and doing confidence intervals and all that good stuff. We got the risk. Now we've got some type of an inspection planning process based off the thresholds. So what does that really mean? Well, let's put ourselves in our shoes 6 years from now as a projected risk result in 2029. So we have our current risk. I picked the beta with the 3.09, for instance. So our current risk is a probability category 4. Our projected risk results now in 2029, risk increases because as time increases, probability of failure increases. So our projected risk results are up in that higher probability of failure threshold. So the organization that would want me to manage this piece of equipment says, hey, we don't really like that. So let's go out and do a highly effective inspection. And based off of that, we want to have a 95% confidence in that inspection. So the inspection plan says, hey, 95% confidence inspection in the tube bundle. So we only want 5% uncertainty. Let's take that as a literal translation. Let's do 95% of the tubes. Let's perform an eddy current. Let's inspect approximately 521 of those tubes. So let's see what happens when we do that projection. Again, here's our tube bundle. We're going to go out in 2029. Let's assume we found the highest corrosion rate that we predicted earlier. Remember, we had 1.3 that we observed, and then we predicted 1.43. Let's just assume we found that. 1.43 mils per year associated to those tubes on that bundle. Well, now we can take that information and again predict some of the results. Remember, we didn't look at every single tube. We're only looking at roughly 95% of the tubes. Let's go ahead and predict what that corrosion rate looks like. So here's our 2029 scenario. We have predicted our corrosion rate based off of our likelihood distribution as well as our wall loss rate distribution. Remember back a few slides ago at the beginning how nodular that likelihood distribution was. It was a small, tight color. Now it's kind of diffuse a little bit. It's a little bit wider, so we have a little bit more uncertainty associated with our results. And remember, the probability function was a little bit closer together. Now it's a little bit wider because we did a little bit less inspection. But if we project out to that 99% confidence interval, we get a corrosion rate of the top 1% of our tubes that's likely going to be around 1.84 mils per year. So in that top 1%. So instead of the 1.43 like we found in 2029, now I'm going to use 1.84. Well, I know that my bundle remaining life is going to be pretty small, and it's likely we're going to have to do something about that. So let's go ahead and consider, why don't we just plug the top 21 tubes that we found wall loss issues with in 2029 as an example. So if we go out and we plug those 21 tubes, we took the highest wall loss tubes, plug those guys up, mechanically sound, hydro tested, all that good stuff. We now have, based on the remaining 1% of our tubes, we have a predicted corrosion rate of 0.63 mils per year, because we're no longer looking at those really high corrosion rates. We're looking at the lower corrosion rates. So that drops us down quite a bit, but notice how tight that likelihood distribution is and how tight the probability of failure, the wall loss distribution is, that density function. They are super tight. So we're very, very confident in all of those results. In fact, they're almost right on top of each other. We have a mean corrosion rate of 0.63 based off of our probability function, and we have our confidence interval of 99% is 0.613, so it's actually less. So in this case, I'm going to just go with the mean. It's higher, but hey, we're super confident on these results. Now, if I take that in 2029 and I project out what my remaining life is for that bundle, I'm actually looking at another 41 years for that bundle. Remember, we were thinking 17 or 13 years previously. We plug those tubes, we do all the analytics around it, we project out what our corrosion rates are, we're getting an additional 41 years, basically 20 years half-life. So our inspection is out to 2049 if we go the traditional route in that case. But let's take it another step further. Let's get into a little bit more math. Sorry, hang on with me. We got a lot going on here. But here's our beta and our etas. Beta is on the left. Notice the beta shifted towards the left. That means we're more reliable, right? So our shape factor is now 2.02 based off of our maximum likelihood estimates. And now looking at the eta, again, it shifted farther to the right. So our eta is now 44.63. So we're moving in the correct directions for both of those parameters for that Weibull distribution. We plug in the Weibull. Notice how nice and smooth that slope is. That's like a nice ski slope if you like to go skiing. That's probably a blue run. Maybe that's why it's a blue color. But hey, that reliability looks great. The black line is where we are with the Weibull today and the probability of failure and the reliability function. The red line, again, remember, that's that probability of 5 category. So we're easily above that probability of 5 category. And we are projecting out quite a bit of life for that bundle. Remember, so here's the risk output based off of that beta and that eta. And then as a reminder, here's the previous results that we had on the exact same bundle, but we didn't plug the tubes, 6 years prior. So there's a lot going on here, but essentially looking back at it, we were able to do optimized inspection planning, predictive results, preventative maintenance on those bundle tubes, and then project out additional life based on the tubes and our projections, all with high confidence.
So predictive analytics and RBI all together.
Thanks, Angela. So here we are. We just ran through quite a bit of math, quite a bit of situations, quite a bit of understanding as far as RBI and tubes and all that stuff. Let's pull it all together and see how did those predictive analytics and those different data-driven decisions, how does that help us with the RBI? In reality, we have a lot more confidence in our RBI results. It's no longer necessarily as gray of a box that we tried to understand the tube bundles from an RBI perspective, as well as, hey, we couldn't inspect those 4 tubes. Now we have an understanding of what they could be with high confidence in those results. So we're then translating that, and that's maximizing the opportunity for that bundle. We just ran through a real world scenario, and in 2029, that's a real world scenario that could exist, where we are again extending the life of our bundle based off of math, real world information from the inspection results, utilizing RBI principles that have been around for a long time, utilizing a lot of math principles that were came up with maybe hundreds of years ago, right? There's a lot of stuff going on here, but we have a lot of confidence in what we're doing and in all those results. Essentially, predictive analytics in this regard has been extremely valuable and helpful for that bundle. Imagine what it could do for all sorts of things outside of the bundles, looking at CMLs, looking at different failure modes and effects analysis, all that good stuff. And using these types of techniques, as well as utilizing a great tool like Antea to help bring it all together, that's good stuff.
Yeah, I agree.
Cool.
All right. Well, Justin, a lot of great information, and I hope you're ready because there's a lot of great questions.
Sure, I can be ready.
So we'll start off with the first one. I'll try to get through as many as I can. There's a lot, but if we're not able to answer now, we'll send answers out to everyone. So what should the corrosion rate be the maximum observed during last inspections in spite of plugging the worst tubes or the lower value calculated after plugging the worst ones?
So let me understand that question correctly. What should the highest corrosion rate be after plugging the inspection? Was that correct, Angela?
What should the corrosion rate be the maximum observed during, I think you're right, yes, last inspection, in spite of plugging the worst tubes or the lower value calculated after plugging the worst ones?
Okay, so we have 2 corrosion rates. associated to that scenario, the 2029 scenario. So we had 1.83 mils per year was the worst corrosion rate that we would find associated to those vessels. So to that bundle. So we did an observed scenario where we found 1.43 mils per year. We then predicted at 1.83, and then that was before plugging. Then once we plugged the highest corrosion, those tubes, the highest corrosion rate that we found was 0.63 or 0.613. So I think that's all the information there. If we want to then play around with some of the scenario as far as, well, we only plugged a couple of tubes, or we didn't plug any, or any of that stuff, those are the numbers that I have associated with those predictions. Hopefully that answered it.
Okay. What are the key parameters and variables that predictive modules consider when analyzing heat exchanger bundle performance?
So there's a lot that goes into it. So when you're building your probability density functions and those kinds of things, you're trying to use as much real world information as you can based on those tube bundles. So for instance, we have a lot of information associated to the same or similar service of those bundles, same or similar corrosion kind of prevention, so like metallurgy, operating conditions, etc. And based off of that, you're trying to build what your density function looks like. From a parameters perspective for corrosion, we're looking at the quality of the inspection. We're looking at the understanding of, do we actually understand how this piece of equipment is being operated and managed? Do we understand the corrosion mechanisms that are associated to that piece of equipment? What type of contaminants are associated to the lines? And all that good stuff. So there's actually quite a bit that goes on to it. And in the background, I didn't really kind of present on that. I really wanted to focus on what mathematical techniques we could use. But essentially, you have to know what your bundle is doing. You have to understand how it's potentially becoming an issue. What type of corrosion are we anticipating? What's the damage mechanism driving it? What type of corrosion damage are we anticipating? So pitting, general corrosion, etc. Once you understand a lot of this, there's a term in mathematics called prior and posterior. You have to have a informed prior to be able to predict how does that corrosion rate actually affect the end of those predicted results. So if you don't have a good corrosion understanding of what's going on with that equipment, you're going to have a lot more uncertainty in the results. So it all depends on the situation, but you can still predict it. It's just your uncertainty. Instead of getting a result of 1.4 mils per year, you might get 6 mils per year, where you go, all right, we don't know enough about this situation because we didn't see that at all. We didn't know enough about the situation, so this prediction is not geared well for that methodology. That was a lot. There's a word vomit, a lot of math and stuff. There's a lot of parameters that go around to it.
Yeah, very case by case driven.
How we can improve confidence level of selected NDE? We face a lot of scaling at inner walls, making NDE results difficult to collect or with lesser confidence.
Yeah, so the inspection technique itself, if you can't determine how your walls are actually being attacked by the equipment and, by the process service and the damage mechanisms associated to it, you have a lot more uncertainty in those results. So if you can't see it, for instance, if you have a heat exchanger bundle that is not inspectable, you have to try to utilize different techniques to understand what the issues are going on within that bundle. So if I perform an inspection and I don't get good results, it's really hard for me to make a determination on what my prediction may be. But if I have a lot of results and equipment with those same kind of characteristics, really hard to inspect, different spiral wound tubes that you can't run an eddy current through, maybe you can't run an iris through it, but I have the reliability data associated to those tubes. Like, hey, we've had 10 tubes or 10 bundles, it's their exact same design. They lasted anywhere from 30 to 45 years, and we had different failure rates. We can utilize that information to try to predict the actual remaining life of those bundles, not necessarily what's going on within that inspection. And based off of that, and this is more the API 581 stuff is really focusing on, it says if you have your reliability data for your bundles, you can use that reliability data using a Weibull distribution to predict where are we on the reliability curve for that bundle specifically, not necessarily utilizing a inspection that you aren't able to see any of those results. There's a lot going on with that, but you can derive assumptions and information with pretty good confidence if you have the data associated to it.
Thanks, Justin. Can you please explain what beta and eta stand for? And if the value is high, is that good or bad?
Good question. So beta is the shape factor. And what that means on the reliability curve is the higher that beta is, the quicker that drop off in reliability will occur. Okay, so the lower beta number, it's going to be a nice smooth drop off. But the higher drop off, higher beta, you're going to drop off from reliability really quickly. Or if you think about it from a probability of failure standpoint, you're going to increase in probability of failure super quick. Versus a lower beta, it's going to be a slower progression up to probability of failure. Now, combine that with eta, which is your characteristic life. That's the expected lifespan of that bundle. So if I have an eta of like 100, that means I have a really long lifespan for that bundle. So if I combine that with a really low beta, it's going to have a nice predictable reliability curve and probability of failure. But if I have a really high beta with a really low characteristic life, that bad boy is going to fail pretty quickly. And we might see that in a lot of bundles that only have 4, 5, 6, 8 years lifespans. They have a high beta with a short characteristic life, or they have an average beta with a short characteristic life. Life is really important. Hopefully that explains it.
Is your probability scale a log scale?
No. Not log. Well, so yes and no. So there's a log normal associated to it, because I'm expecting for my corrosion rates, the majority of them to be close to 0. And then I'm expecting some of the higher rates, there's going to be less towards the higher end. So I'll use a log normal for that one, but some of the other ones I'll use a normal distribution.
In short, during bundle analysis, the financial consequence is a leading factor for risk calculation and decision making comparing with area consequence. Is my understanding correct?
So yes and no. When it comes to a bundle, it may not be associated to area, just depending if you can have a catastrophic issue with those two different processes mixing. For bundles, it'll come down to financial consequence and efficiency and production loss. A cost benefit analysis is recommended when you're looking at your consequence of failure for your bundles. So is it better if we lose efficiency in this bundle? For instance, let's just assume we plug 50% of our tubes. Are we okay with the loss of efficiency based off of where we need to go for production rates? How much does that bundle cost to replace completely? Is it replaceable, or do we have to replace the whole exchanger? How much is the maintenance on plugging all of those tubes? If we're okay with not having to worry about doing all those tubes and we can get a replacement bundle, a lot of that goes into your cost benefit analysis for your bundles, which then provides you the information of your consequence of failure, which becomes a dollar amount at that point. So if you can buy a bundle for $100,000 and replace it, within $200,000 is your total budget, but you can plug it and it's only going to cost you 10 to 20 grand to do that plugging, you might find that risk and cost benefit is going to lead you one way or another.
Good answer. Does the RBI take into account the type of damage mechanism, pitting, corrosion, erosion, or baffle fretting, or are end-of-life calculations solely based on percentage loss over time?
So it'll depend on your bundle. With this one, I used a general corrosion damage mechanism. I didn't do a predictive analysis on the pitting, for instance, and I didn't look at baffle plates or anything like that, because we know about this piece of equipment. We know how it's going to fail. We understand the damage mechanisms associated to the shell side and the tube side, and this one was a good, clean scenario for us to kind of show how the predictive analytics can work. But yes, it does take into account how do you can't necessarily predict off of any current if you don't understand how that bundle is being affected and being attacked. When it comes to like pitting corrosion rates and those kinds of things, you can predict how much of a pit you may see when it comes to those bundles, but you have to have the data and the information and the informed decision when you start doing your analysis. So damage mechanisms is very important. You have to understand how it's going to fail.
What if we found manufacturing defects like mechanical dents during tube inspection?
Yep. So depends on how many defects we're finding. Those are kind of the tubes, like for instance, in our scenario, the tubes were not inspectable. So typically we in a likely scenario, we would just plug those tubes because we can't inspect them and there's only 4. and we would run with the remainder of that bundle and understanding how we're going to be able to predict our remaining life and all that stuff. One of the things that I didn't really jump into in the presentation today is in 2023, when you do that inspection, you find those 4 tubes, let's plug those 4 tubes, let's not even risk it. But then how many more tubes can we plug to extend the life of our inspection? So and I did that in the 2029 scenario. If they ended up plugging 21 of the tubes, that extends your life to that 41 years. So a lot of the times, and this is where we're trying to get a little bit better as far as evergreening and managing how we're doing the follow-up work from inspections. A lot of times we need to think a little bit outside the box. Okay, yeah, we'll plug those 4 tubes, for instance, that had mechanical defects or bending of some sort. But could we plug some more and, again, extend that asset's life so we don't have to go and worry about it in 5-6 years from now?
One more question, Justin. Corrosion rates can vary with time. How are you and this software accounting for it? The examples seem to suggest that uniform corrosion rate assumption.
Correct. The example did assume a uniform corrosion rate. Lots of different ways to be able to manage how those corrosion rates may or may not change. Corrosion studies, corrosion control documents, and integrity operating windows are highly, highly important to understand how that damage mechanism is being affected by its operating conditions. Throughput, for instance, if you're ramping up throughput, if you're understanding the different parameters, let's say we change feeds, let's say we have a different corrosion inhibitor, all of these things factor how these corrosion rates may or may not affect our equipment. So in the assumption, we are assuming, hey, we're operating like we've normally operated. Our feedstock hasn't changed. We're not increasing number of chlorides, for instance, in our stream or anything like that. But a way to prevent and or predict how your corrosion rates may be affected associated to the operating life of that vessel, setting up integrity operating windows, making sure you understand the contaminants associated to those process streams. Pressures and temperatures make a difference when it comes to corrosion and damage mechanisms. And being able to have all of that as a complete picture is going to help you with your predictions.
The only thing that would change that, of course,
All right,
if you had a process change or if it was a batch operation, all these things come into play during this whole process.
Correct. Yep.
Thanks so much, Justin and Floyd. We have 50 questions, so we have some work to do after this and get all these answered and sent back out. But that is all we got for today. But if you would like to learn more, you can go to www.antea.tech. We have a lot of great resources on our website. I also have some great news. We will be having another Asset Integrity Summit, and it will be in Houston on November 3rd. So please keep an eye out for the invite. I know we wanted to give everyone a heads up because some people wanted to travel last time and there was a short notice. So we're trying to get all that information out there pretty quick so everyone can plan travel. This will be a great educational event, of course, for our industry, and it is completely free. If you would personally like to receive more information from myself, Justin, or Floyd, please send us a direct message on LinkedIn, and we'd love to hear from you, and we'll get right back to you. Thanks, everyone. And as always, we are so happy that you could join us, and looking forward to our next webinar and seeing you all guys there as well.
Thanks, Justin. It's really good information.
Thanks, guys. Enjoyed doing it. Let's do it again.
Yeah, soon.